We're looking at the last of the four conservation equation in this recording. We've covered mass conservation, which leads to the continuity equation, momentum conservation, which leads to the momentum equation of the Navier-Stokes equation. Then we moved on to the energy equation. I'm showing this slide again to go back to that formulation we start from all the time. That is, we're looking at an equation. On the left-hand side, you've got, if it's positive, rate of increase of the conserved quantity in the fluid contained within the control volume. And that needs to be matched with a rate of increase in the amount of energy stored by the fluid inside the control volume. So if you've got a net positive addition of, in this particular case for this slide, energy into the control volume, then it must be matched by a rate of change of the energy, which is positive. And we're going to adopt a similar, more or less the same form of equation in order to present species conservation. So let's skip to that part of the slides. Here we are. So we're looking at something very similar. What we are looking at on the left-hand side is the rate of addition, if positive, of species A to the fluid contained within the control volume. If this is positive on the left-hand side, it has to be positive on the right-hand side. And that term on the right-hand side relates to the rate of change of the amount of species A stored in the fluid contained within the control volume. So positive input has to be matched with a positive rate of change, that is a rate of increase in the species A. So this type of equation is used to track at any given point or region in space and the evolution of a species in a mixtures of multiple species. So as an example, we have something here to illustrate what happens, and we've used that example in the slides of the introduction to show what happens to species as it mixes within a volume. So imagine you've got a container shown here, which initially is not as shown right there, but initially you have species A only on the left-hand side, and species B only on the right-hand side. You've got a membrane separating these. The minute you remove that membrane, you will get a diffusive transport, convective transport. That is, you'll get both molecular diffusion of species, for example, B into the volume occupied by species A, and vice versa. And on top of it, differences in concentration will set up probably variations in densities that may lead to essentially natural convection, that is motion of the fluid, which leads to a different type of mixing called convective mixing. Okay? On the top here, to illustrate these effects, that is to illustrate the fact that you've got varying both in time and space concentration, we are showing the way concentration can vary over space. But also, if you were to record this at different times, you would get a graph that changes with time. So you've got variation both over space and time. Concentration of a species in a mixture can be written in terms of molar concentration. That's what that capital C letter refers to. But you could also use mass concentration. So mass concentration would be written with the Greek letter rho A for the mass concentration of species A. Mass concentration would be written in SI unit as kilogram per meter cube, but for the species A. So for example, rho A would mean how much of mass of species A only you have within a certain volume. So if we go back to that conservation equation, the first two terms represent the net rate of increase of species A in a region, which is the control volume. So you could take a small volume here, a small square, and we would track the amount that goes in and out of that control volume with open boundaries around it due to diffusive of convective transport. If it's positive, it means you've got more going in than going out. Simultaneously, you will get both processes, flow into and flow out. But if the balance is positive, it means you've got more going in than going out. So essentially, the convention is that if this term is positive, it means it goes in, but it can also become negative. And if it becomes negative, it means it's actually going out. And you could have put it as a positive outflow. So this is transfer through the boundaries of the control volume. And then you've got the rate of generation of species A, possibly due to a chemical reaction. So if you have a chemical reaction that transforms, for example, species B into species A, then you will get a rate of addition of that species A within the control volume, and that's what that accounts for. If the combined effect of transport and generation within the control volume is positive, then you've got a positive rate of increase of species A's within that control volume. The discussion that I just had did highlight the fact that you can have convective, which is also written advective transport. So you can have rate of input of species A into the control volume by advection or convection, same thing. And you can also have the transport due to diffusions. That's what diff stands for. So you have input and output, and I just realized now that I've got a typo here. I'll correct that. That should be the rate of outflow. O stands for out, I for in. So therefore I must correct that and put this as an outflow. So these are just essentially breaking down each of these terms into the two modes of transport. So if you start from that general expression, you can, by going through a number of manipulations, which are outlined in the lecture notes, you can derive the actual species conservation. So you have just an example here. First of all, on the right-hand side, you've got a sketch of the control volume, which is square. You will get transport by convection and or advection, written here, and diffusion through each of the phases. Remember, you've got a transport through a phase only if the flux or the direction of flow is perpendicular. If you've got a non-perpendicular component, it will be tangential to the phase. Anything that is tangential is not going to go into the control volume through that phase. So the only component that matters to us is the perpendicular component. If it's at an angle, just extract that component. So when it comes to the flow into the control volume by advection, what matters is the x component of the fluid flow, x being aligned with the horizontal faces. So the x component is written for velocity vector u. It's the only component of flow that will matter when it comes to convective transport. So we need to look at the rate of mass transport of species A only. So it's very similar to mass conservation, except that instead of writing the density of the mixture or of the liquid, we'll write the density of the species A only. So you've got a certain amount going in there. You've got a different amount going out due to the rate of change of rho and u, so this. In fact, when you look at the balance of in and out, what matters is the rate of change of rho u. So this is something we've discussed in the context of mass conservation. You've already seen it, and it's described again in the lecture notes. I'll refer you to that. The species transport going in and going out, so that's through phase X here, and through phase X plus delta X, this phase, we end up with this net influence. The sign is different because diffusive transport is determined as being the opposite to the direction of the density gradient. So you've got a minus sign here. So we end up with a minus and minus gives you a plus. That's the reason for the change. So I'm not going into the details of this, except, and we've seen that already, that Fick's law is what governs mass transfer in a mixture, in a binary mixture like that. So we need a coefficient of diffusivity, which is written DAB, where you have a mixture of species A and B. And we're interested in the transport by diffusion of species A only. And what determines or governs that gradient in the direction, or that determines, that transfer by diffusion in direction X, is the gradient of the species density in the direction X. So when we combine these, and we do it for both the vertical and the horizontal direction, you put it into the conservation equation, you end up with your governing equation, which is very similar to the mass conservation equation we would have studied before, but you do have both diffusion and convection transfer, and you have the possibility of a rate of generation. This is detailed a little bit more in the lecture notes, so I'll refer you to the lecture notes for that.